So welcome back. You know, do you know how to tell if this is just? How do you know how do you know two vectors are parallel? Two vectors are parallel. I think I've stated this, but it hasn't come up too often. Do you know what? How do you know if two vectors are parallel?
Wouldn't they have to end at the same points at least two coordinates, or like vertically and horizontally?
Well, I don't know if I like that.
The 3 points have to be the same, right?
What'd you say?
The 3 points have to be the same.
Well,
They just have to have the same slope.
well, that's sort of true. Parallel, I mean, back in the day, parallel always means have the same slope.
Yeah.
But in a way, when we talk about vectors, we don't use the word slope that much, except we almost did the other day a little bit. But you're sort of onto something. I don't really use the word slope, but they have to have the same
Angle.
rate of movement. Right, they got to be sitting at the same angle. There you go. Do they have to be the same length?
Yes. No.
No. See, they can be shorter or longer. See, really it comes down to this, and it really comes down to this. Two vectors are parallel. Two vectors, u and v, are parallel if u equals k times v, where k is some scalar. Now, so you guys were kind of, as you were thinking more geometrically, I'm thinking more mathematically. This is what makes two vectors parallel. I mean, if you've got this vector u, 3, -1, 2, can you come up with a parallel vector? And what I'm saying is, here's what I'm saying. Here's what this says, and here's how you say it in word easier, is any scalar multiple is a vector, is a parallel vector. Any scalar multiple. So multiply it by 6, it's 6 times as long, but it's pointing in the same direction. We call that parallel. Multiply it by 2, it's twice as long. We had that discussion the first day last week. But we call that parallel. Multiply it by -1, it points the other way. 180 degrees opposite, actually, but we could call that parallel. Actually, there's a little phrase called anti-parallel, but I won't ever use that word again. I think I would call that parallel. Any scalar multiple, it makes it parallel. So multiply it by 1/5, it's parallel. And it's 1/5 as long, by the way. But we're not, when we do that, when we do scalar multiplication of a vector, we are just changing the length and we're not changing the angle. So maybe that makes you realize, yeah, dude, they're all parallel. So if I had to come up with one, I would just, there's millions of them, but there's one, right, you guys? Mm-hmm. They're parallel.
So
you know what's funny is if you drew them, but if you drew one, and so there's a picture of you, and then that's not this you, sorry, now I went to a two-dimensional picture for a minute. These are 3D vectors, but I went to a two-dimensional picture for a minute. So then if I had 2 times u, like I said, it would be 2 times as long. You know, watch, when you draw 2 times u, it would be 2 times as long. You know, it lands right on top of u. I mean, these scalar multiples, I'm using the word parallel, but again, the funny thing is, when you draw them or depict them, they're all landing on top of each other. They're just longer or shorter, especially if we all draw them starting at the origin, like we're kind of supposed to. So in a way, maybe that throws you off. Well, no, that's not parallel, they're just on top of each other. Well, that's parallel, though. I don't know, they're just not off like this, right? You don't usually, but you can move vectors and put this guy up here. You can start them wherever you want to start them. But a scalar multiple is what makes them parallel. I mean, that's good. I drove that out. I overdid that, probably. You know, I was watching my videos. I was thinking, one of my faults on my videos is I shouldn't say this. I over-explain. I really over-explain. Now, you guys are students. Maybe you like that. But if you're catching on to things quick and easy, then maybe you're not. Like, I mean, I'm over-explaining, but it's okay. I am a teacher. Maybe I'm supposed to over-explain a little bit. But maybe it just strikes me that way because I know it all, you know. Anyway, we didn't know that. Parallel vectors are scalar multiples. And then what happened, we went into class, we went into 11.3 and we learned about the dot product, and I'm just going to review maybe a couple of thoughts. Do you know how to do a dot product? Look, here, let's do, there's a u and a v. Well, let's not do those. Here, sorry, let's do another u. Here's another vector u, 2, 4, -6. Here's a vector v, 5, 1, 7. I mean, can we do the dot product of u dot v? And I told you how to do it. Do you remember how to do it?
You just multiply the x's, y's, and z's and add them to a scalar.
Good. You multiply the x components, the y components, the z components. You multiply them correspondingly like that, and you add them all up, and you get this number, which is a scalar, like you said. Good. So what is it? It's 10 plus 4 minus 42. I guess that's a -28. So what? And then I don't have a lot of great meaning for that number by itself, but this dot product shows up in some other formulas. It shows up in this thing called the projection of u onto v, which is kind of interesting, but I don't think I want to talk about that. It shows up in this formula. I did highlight this formula. The cosine of the angle between two vectors is u dot v over the magnitude of u and the magnitude of v. So I called your attention to this formula. This is useful. And then we said this right at the end of class, I guess. It might even got off the video there. Right at the end of class, one of the cool ideas that comes out of this is the angle between two vectors. And so just when you put the two vectors tail to tail, they kind of form a plane, and it's the angle between those two vectors. And it could be an acute angle, it could be more than 90, it could be an obtuse angle. We never, could be 180, I suppose. If they're directly opposite each other, it would be 180. But what if it's 90? And if it's 90, what's the cosine of 90? What if, in other words, what if the two vectors are perpendicular? Then this angle is 90. If the two vectors are perpendicular, the angle is 90. If the angle's 90, what's the cosine of 90? 0. How does this fraction become a 0? This fraction becomes a 0 when the numerator is 0. So we just stumbled into this cool idea that two vectors are parallel if they're scalar multiples of each other, but two vectors are perpendicular, u and v, are perpendicular if u dot v equals 0. So to me, that's kind of one of the most important concepts of the dot product, is kind of this. I mean, there's some other, I can find other angles, but just this falls out. When are two vectors perpendicular to each other? How can you test to see if they're perpendicular to each other? When their dot product is 0. So that's important. That's important. By the way, there might be some new words for you here. And so this kind of fell out of 11.3, fell out of the dot product. But together, these are a couple of good ideas. This was stated earlier in 11.1 or 11.2. Hey, another name for perpendicular is orthogonal. Have you ever heard that word? Orthogonal. I don't know. It's maybe a new word. It means perpendicular. Here's another word that means perpendicular. Normal. why do we need 3 words? We don't really need 3 words. I do want to, I'll just read this to you though. I want to make sure I read this correctly. The terms perpendicular, orthogonal, this is in the book, a little remark. The terms perpendicular, orthogonal, and normal all mean the same thing, meeting at a right angle. But it is common, however, to say that 2 vectors are orthogonal. Okay, so in a way, I used the wrong word here. It's common, well, again, they're all the same. But when you're talking 2 vectors, they say use the word orthogonal. They say, hang on, 2 lines or planes, we use the word perpendicular. That's true. Back in algebra, when we talked about lines, we would use the word perpendicular, or planes, or perpendicular. And when we want to compare a vector to a line or a plane, then we use the word normal. And so if we have a plane and a perpendicular vector to the plane, we sort of call that normal to the plane. Anyway, it's perpendicular to the plane, it's normal to, I mean, anyway, they're telling me when to use the right word. The truth is, I kind of don't care, but they're all the same word in a way, but there is a context where it's more accurate, I suppose. You know, this is a big important idea though, this normal to the plane idea, and that we get here, we build toward this, and this kind of culminates in 11.5. Of course, I haven't really got to 11.4 yet, but we'll be discussing planes and perpendicular vectors to a plane, normal vectors to a plane. And maybe this idea helps. Their 2 vectors are perpendicular if their dot product is 0. Hey, so could you just, watch this. This is kind of fun. So here's a vector. Can you find me a perpendicular vector, please? Here's a vector. Can you find me a perpendicular, maybe I should use the word orthogonal. Orthogonal. I like that word. I was thinking of naming my son. Isosceles Orthogonal Smith. Chickened out. It would have been a cool name though, right? Can you find an orthogonal vector or a perpendicular vector? Can you just, well, here's the deal. The dot product needs to be 0. The dot product needs to be 0. You know how to do a dot product. Can you just think this through and figure this out? How do you come up with an Anybody?
We need the magnitude of u and v.
Not really. Hang on now. Okay, to be orthogonal, this is 90 degrees. The cosine of 90 is 0. The numerator needs to be 0. To be orthogonal, it comes down to this. The dot product is 0. Oh, I think I know what you're saying. You're saying in order to do a dot product, you need, yeah. He's thinking in order to do a dot product, he's thinking of this alternative formula. You know, the dot product is the magnitude of u and the magnitude of v times the cosine of the angle between them. Are you following me? You follow that little bit of algebra there? If I multiply these over to the other side, here's an alternative form of the dot product. If you know their magnitudes and the angle between them, you can do a dot product. Hang on, but we just did a dot product this way. How did we do this dot product? Multiply the x's, y's, and z's and add them up. See, the other formula for a dot product is, u1 v1 plus u2 v2 plus u3 v3. I mean, if you have the components of the vectors, I think you do a dot product like that. If you have the magnitudes of the vectors and happen to know the angle, maybe you do a dot product like that. We tend to do dot products like that, and then we tend to use this formula in this form to find the angle. That's what we tend to do. So anyway, can you just multiply the x's, y's, and z's and give me, I need it, if it's orthogonal, I need it to come out to be 0. What do I need here?
3 and 5.
Thank you, 3 and 5. Whew. It was like pulling teeth. I think that works though, right, you guys? If I do 15 and negative 15 will add up to be 0. Awesome. Is that the only answer? Is there another answer?
Negative.
Oh, the negative of him, which would be negative 3 and negative 5. Hang on, because that would be negative 15 and positive 15. Yeah, that would be 0. Right. In 2 dimensions, there should be 2 answers, I suppose. This is the vector 5, negative 3. It goes over 5 and down 3. Here's the vector u we're talking about. Sorry about my picture. That's vector u. In 2 dimensions, there are 2 perpendicular vectors. There's that one and that one. Right? Well, 2 basic perpendicular vectors. Of course, you can make those guys longer or shorter. There's actually infinite numbers of those if you make them longer or shorter. And there's infinite number of those if you make them longer or shorter. That's not the point. There's 2 perpendicular vectors, you could say. So anyway, it's not hard to just use a little math and make the dot product be 0. After doing this, though, in 2 dimensions, you kind of stumble into this little catchphrase. If you want a perpendicular vector, orthogonal vector, what I do is I switch them and negate 1. Did you hear that? Switch them and negate 1. So hang on, did I do that? I switched the negative 3 and the 5, and then I negated him, which made him positive. Let me try this. Switch the negative 3 and the 5 and negate him. Right, that's my 2 options. Switch them and negate one of them. Gives you a perpendicular vector. So that's cool. That's a little switch, but that's in 2D. In 3D, that doesn't really work. Let's just try this. Can you find a perpendicular vector to him? This is in 3D now. So I need something perpendicular, or I'm sorry, orthogonal to you. I want to find something orthogonal to you. I just want to make this up. I want to just do it in my head. I know it's a little tricky, but it's not that tricky. I just got to make a dot product that comes out to 0. I got to come up with a dot product that comes out to 0. And so I just try something actually with the 2, 4, and 6. This is pretty darn easy. I think I can go with, I just stumbled onto something. I think 1, 1, 1 works. Because isn't that 2 plus 4, which is 6, plus negative 6, which is 0. You multiply the x's, multiply the y's, you multiply the z's, and add them up. If you get 0, they're orthogonal. I just stumbled onto one real easy. Guess what? When you're in 3D, how many perpendicular vectors are there? There was 2. Remember there was 2? In 2D, there was these 2. In 3D, how many perpendicular vectors are there to this guy?
Say infinite.
Here's 1. So I heard somebody once said 4, because there's this one, there's that one, and that one. But once you start thinking about 4, why not that one, and 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 that one. In fact, everybody that's in this plane is perpendicular to this guy. So you're right, there's an infinite number of these perpendicular vectors in 3D. So the fact that I found one so easy wasn't that much of a miracle. There's millions of them. Watch, let's just try another one. I don't know what to call this, something else. But let me just see. I mean, now, let me show you. How good is, well, let's call this one, I don't know, let's try 3 and negative 1, and then I don't know what to do with this one. Call it A. Well, watch then. You can use this dot product. Let me think here. So I got 6 and negative 4, and then I got negative 6a. Are you guys following me? You multiply the x's, the y's, and the z's, and you add them up, and what do you want it to be? 0. So you can do a little algebra like this if you felt like it. You can pick any two and then call the third one an unknown and do a little algebra and find it. That's one way to do this. That's a 2. Move the 2 over, it's a -2. Divide by -2, I mean -6. So I guess A is a 1/3. If A was I just kind of algebraically figured out if those two were this, and I just threw them in there. If those two were these numbers, the third one can be algebraically figured out to be 1/3. Since there are infinite number of these, that's an approach that works. This guy is perpendicular to him. He might not be perpendicular to him, right? Orthogonal to you. Here, try this one. Can you get one orthogonal to V? Anyway, the switch and negate one doesn't really work. I mean, that only works in 2D. I mean, now we're in 3D. You can't, well, unless you wanted to be kind of a smart ass. I mean, what if you switched to negate one? What if you went switch and negate, make that 1 and 5, -1 and 5, then what would you do with this guy? I did switch and negate. So I got -5 and 5, that's 0. What should I multiply by to get this all to add up to 0? 0? Yeah, that works. I mean, that works. That's a 3D vector that's perpendicular to him. It sure is. Why is it perpendicular? This important idea. I don't know, some of the questions in the book might be, here's two vectors. Are they perpendicular? So then you do the dot product and test them. I'm doing something different. I'm making you, can you come up with a perpendicular vector? Can you find one? And it's, like I said, it's not too hard. I'm still using this dot product. Well, good. So, I don't know, I'm reviewing a few thoughts. Maybe I spent a long time on that topic, but I did it thoroughly, and like I said. So I think I'll move into 11.4 and introduce you to this cross product, and we use this a lot. So we're going to get introduced to this, but we use this a lot in 11.5. We need this cross product. So it's a different type of multiplication. It's called U cross V. It's a different way of multiplying two vectors. Listen, I'm going to teach you how to do it, but first I'm going to tell you what it is. If you have two vectors in space, there's U. There's V. And again, when I draw it on the blackboard, you know, it looks like, oh, those are 2D vectors. You're on it, but I'm trying to pretend I'm in space. I'm actually just up, but I'm on a 2D whiteboard. So this is just two vectors. When you do their cross product, this is what you get. You get this third vector that's perpendicular to both. That's important. And by the way, when you do a dot product, you get a scalar. You get a number, 0 or 17 or whatever. When you do a cross product, you get a vector, but it's this vector. It's perpendicular to both original vectors. So the right angle is right here. Makes a right angle with him, and it makes a right angle with him, perpendicular to both original vectors. So U cross V is a vector. I'm just going to say, I guess I'll just write this sentence, is a vector perpendicular, or I guess I should say orthogonal. I'll just keep going here. Perpendicular to both U and V. So this is U cross V. I mean, you could call him W or whatever you want to call him. He's a third vector. He's perpendicular to both. And And the context where that'll come up usually is this. Let me just say, I mean, I'm going to be heading into 11:5, you know, again, probably Friday or so, but here I'm previewing it. Listen, when you have two vectors in space, when you do put their tails together, then they do form a plane. And so two vectors with their tails together basically form a plane. They form a plane. And now, when you do this cross product of those two guys, you get a vector that's perpendicular to the plane. That's kind of the big important idea that's coming up. That's kind of the big important use of the cross product, to get this perpendicular vector to this plane. That's our important use of the cross product in our class here, coming up at 11:5. Looking for this perpendicular vector to a plane. So there you go. They say this, so I said this, that they kind of have some properties of cross products. They say this about your cross product. You might have heard this in your physics class. They say U cross V, or actually the magnitude of that U cross V is the magnitude of U times the magnitude of V times the sine of the angle between them. That's kind of similar to our dot product formula, but it's different. It's the cross product formula, and I just want to caution you, is this how you do the cross product? Well, this is how you do the magnitude of the cross product. I mean, this is the length of the cross product vector. Right. What's theta? Theta is the angle. I gotta say this. Theta is the angle between U and V. This will happen. We never try to. We try to avoid this actually. If you happen to cross product two vectors and you get 0, which means like 0, 0, 0, you'll get zero, the vector 0, which is 0, 0, 0. That happens when U and V are parallel. Sorry, that happens if U and V are parallel. Now, do you remember earlier today we said, how do U and V become parallel? How are they parallel? Remember what we said? Parallel. Why are they parallel? Or what makes them parallel?
The angle between them is 0.
The scalar.
Well, yeah, the angle between them is 0, which means they're laying on top of each other. You're right about that.
They're multiplied by.
I said it another way, though. They're scalar multiples of each other, right? So I'm just going to say if U and V are scalar multiples of each other, this is the way our book says this. But that means they're parallel, scalar multiples of each other. Right. But you're not wrong to say the angle between them is 0. That's true. Because they're on top of each other and they're scalar multiples and they're parallel. Right. This is a funny little property. Now I'm showing you this, and the truth is I don't hardly ever use this formula. I think you might in physics, and this pops up occasionally. And then what's this other one? Yeah, this other one's kind of weird. It kind of relates to this. The magnitude of U cross V is the area. Look at this. It's the area of the parallelogram. Parallelogram formed by U and V. Now there's some proofs of these, and that would be fun mathematical exercise to prove these formulas. I'm not doing that. But I'm calling your attention to some of these ideas about a cross product. These are some initial ideas about a cross product. And that last one really kind of, I don't know, the proof would be interesting because it kind of blows me away. Because first of all, do you understand the parallelogram formed by U and V? This might have slipped by you over the first few days of class. when you have these vectors u and v, I mean, here they are. You know, we talked about adding them and getting the resultant. Well, and when you add them, you put somebody's tail on somebody's head, and so if I took u and put it on, I mean, so when you do that, or that's adding u to v, but you could also add v to u. I mean, when you do add vectors to each other, they sort of form this parallelogram, and then we did this to talk about the resultant. Okay, but forget the resultant. I'm just forming the parallelogram, and look what it says. The area of that parallelogram is equal to the length of that vector. The area of that parallelogram is equal to the length of that vector. Now, there's probably, I don't know. Yeah, that's nothing you can see. If you want to see that or understand that, you got to dig down into a proof of this, and maybe the book has one, and you could try to follow the proof of why the math that followed this. It probably has to do with, geez, I don't know. I haven't looked at that proof in a while. The law, I was thinking the law of cosines might help. That might not be true, but it might. Anyway, kind of interesting. The area of the parallelogram is the length of that vector. But not that important to me. Sorry. It seems like the most important thing to me up here is this. What is the cross product? It's perpendicular to both original vectors. And now, what else is important is I need to teach you how to do it the way we do it in this class. And we do a cross product sort of with this trick. We sort of do a determinant. I'll show you. Here's what we do. Let me, here we go. I'm going to do a real problem. If I give you a vector u, 3, -1, 4, and I give you a vector v, -2, 4, 5, okay? If I want to do their cross product, u cross v, then here's what I do. I make a 3 by 3 determinant. I make a 3 by 3 determinant. Across the top row of the determinant, I put the I, J, K. They're kind of the little, just the little placeholders in a way. But those, you know what those are. Those are my standard unit vectors in the X, Y, and Z direction. And then across the next row of this 3 by 3 determinant, I put U. I mean, so if it's U cross V, then I do U next. Here comes U, and here comes V. Okay, and then I do this determinant. Now that takes you back to pre-calculus, perhaps, but I'll remind you. How do you do a determinant? There's a few ways to do a determinant. There's a couple methods. One method of doing a determinant is called expansion by minors, or cofactors, or some, anyway, here it is. Here's what you do. You grab any row or column. I'm going to grab the top row. You grab that element I, that element I, and what you do is you sort of cross out that element I. You cross out his row and his column. I'm going to sort of do that. And multiply him by his little cofactor, or his minor determinant here, which is this little 2 by 2 determinant, -1, 4, 4, 5. Now, let's pause a second. Do you know how to do a little 2 by 2 determinant? They're the easiest one. They're easy. But you got to remember how to do it. You multiply this diagonal and subtract that diagonal. So it's -5 minus 16. I'll write that down for you. Times I, so that's a -21I. Now we're not finished. I got to continue on this row. So now I go to J. The next element is J. I got to do his minor determinant times J. When I do J, listen closely, it comes with this automatic negative sign. Don't argue with me, just write the damn thing down. J comes with this automatic negative sign. I'm putting it in red. High alert. Danger, warning, danger. Don't forget the automatic negative sign. And then I do his minor determinant. Now what's his minor determinant? I cross out his row and his column. So now crossing this out too much kind of messes you up. I mean, I'm doing this real slow and easy this first time, by the way. But his minor determinant then is 3, 4. Are you following me? I crossed out his column. It's 3, 4, negative 2, 5. Let's do K. K is a plus sign. I'm going to do K now. And he has a minor determinant times K. What is K's minor determinant? When you get to K, you cross out his row and his column, and you do this minor determinant here. That's 3, negative 1, negative 2, 4. How you guys doing? I mean, that's the long, slow explanation of how you do this. It's taken me a while because I explained, but when you actually start doing them, you can speed this process up a little. And I'm writing all this down. The truth is, when I do this in the future, I won't write all this down. I think I'll kind of do this in my head. But here we go. We'll finish it here. This next J term then is I got to do this determinant, which is 15 minus negative 8. You got to watch this subtraction. That's a 23, but it is, but there's this automatic negative sign in front of it, so that's negative 23J, I think. I mean, the determinant was a positive 23. I think the automatic negative sign made it negative 23. 15 minus negative 8, right. 15 plus 8, 23, negative 23J. What about the K? 12 minus 2. 12 minus 2. Double checking myself there. 12 minus 2 is 10. 10K. And then here I am. See, and so you know me. You have I don't use the I, J, K notation too often, but I need to here. I mean, it's my guide for getting through this cross product. But to tell you the truth, now I'm at the end of this. This is the cross product. This is the answer, and I like to write it back my way here. I mean, here it is, right? It's that vector, and that's perpendicular to both those original vectors. I mean, I guess I could check that. How would I check to see if he's perpendicular to both original vectors?
Multiply them using the dot product.
The dot product should be 0. If I wanted to check that, I won't even bother. But yes, the dot product with him should be 0. The dot product with him should be 0. It's just like this picture. I got a U and a V, and this answer is perpendicular to both, shooting out of the plane contained by both. Yeah, pretty cool.
Is the cross product between vector u and v a resultant, or is that just different sorting?
Yeah, I think I save the word resultant for when I'm adding vectors.
Okay,
And if I'm adding u and v, I draw the parallelogram and I do this thing, which is not u cross, no, it's different. It's u plus v. And I save the word resultant for adding vectors. And this is not. This is multiplying vectors in this new weird way. By the way, the cross product is not commutative. U cross V does not equal V cross U. It's not commutative. U cross V is not V cross U. In general. But let me show you how close to being commutative it is. What you actually get, so if I did V cross U, and how would it change if I did V cross U? I'd have, if you remember, I wrote U and V here, so I would write V and U here. I would change the order here, and I would get the exact same numbers, but it would be negative. I'd get positive 21, positive 23, and negative 10. So the truth is, they're not commutative, they're different, but if I'm cross-producting these two vectors, one of them is this one, and the other one is that one. If I have two vectors on this whiteboard, one of them, the cross product shoots out at you, and the opposite cross product shoots into the other one. Right. Right, they're opposites of each other. And in our math class, for the purposes of what we're doing, usually we're looking for that perpendicular vector, and we don't care. We don't care if it's that one or that one. For the purposes of physics, they get worried about that. I mean, in physics, those cross products mean something, and it's important to know which way that vector points. And so they use the right-hand rule. Let me help you a second. So if I did, look, now I am pretending this is 2D, and this is U and V. And if I do the cross product, then the cross product is going to shoot out at me, because this is a plane that they're contained in now, or it's going to go into the board. And the right-hand rule tells you which one. Watch. So let me think. If I'm doing U cross V, I use my right hand. Don't use your left hand. For the right, it's the right-hand rule. And if I do U cross V, I need to put my fingers like on U and curl them toward V. And that makes, when I do that, that makes my thumb is pointing that way. So U cross V is into the board. If I was to do V cross U, keep your right hand, I need to put my fingers on V and curl them toward U. And therefore, so V cross U would be this one coming out at you. So in physics, they use the right-hand rule, and it means something. But we're just doing math for fun. And in physics, it doesn't seem like they actually do this, because it kind of sometimes seems like you're not even messing with components too much. Again, back to your physics class, it seems like a lot of times in physics, maybe you have the magnitudes of the vectors, and you have the angle in between them. And so maybe this is how you do a cross product. Of course, but then you're not really getting the cross product, you're actually just getting the length of the cross product, which is maybe all you want, the amount of force. You know, and maybe you don't really care about the 2, 12, 18, but you just want the amount of force, whatever that magnitude is. I don't know, just, you know, it's a different class. They do things a little differently. The concepts are still concepts, but it depends. Cool. Let's just let's try another one. V is I don't know. Let's just see what happens. So I'm going to try this again. I'm going to do U cross V. So really, when I do these, I feel like I got to write them down. I write down my determinant. I do the I, J, K. I mean, I write this all out, and I do U cross V. So I'm going to do U cross V. But now watch me. Instead of writing all that out that I did over there, I'm going to do it in my head, okay? So, so watch me a second. I mean, you can do it with me or whatever, but so I'm doing I. If I'm doing I, like I said, I cross out his row and column. I don't really want to cross it out. So I do his minor determinant. His minor determinant's right here, and it's 12 minus 15. Right, you guys? 12 minus 15 is -3. That's it. The next one is J. I'm crossing out his column, so I'm doing 6 minus 12. 6 minus 12 is -6. Don't forget the automatic negative sign, which makes it +6. And then finally K. 5 minus 8. 5 minus 8. Negative 3. And that's the cross product of those two vectors. I mean, it's not, again, I drug it out and explained it all to you, but there it is. You kind of can do some of that subtraction in your head. You know, it is funny, I warned you, this class, this chapter doesn't involve a lot of calculus. I'm not doing terrible integrals. I'm not doing terrible derivatives. I'm doing subtraction, though. I'm doing a lot of subtraction, and believe it or not, you better practice that. I mean, I don't know. Don't get overconfident, please. Please practice it. Hopefully, don't make mistakes. I mean, people make mistakes. And then when I grade the test, I get a little frustrated. And I look, am I grading your calculus 3 concepts, or am I grading your subtraction skills? You know, I mean, anyway, I take off points because your subtraction skills suck sometimes. But I try to give you a little credit for knowing something. This automatic negative sign, I don't know. I can't. I'll just explain it by saying, when you do this thing called expansion by minors, these elements they come with these signs attached to them. So this is plus, this is minus, this is plus, but they alternate. So this is minus, this is plus, this is minus, this is plus, this is minus, this is plus. And see how they all kind of alternate. And so if you happen to be expanding on this row and crossing out that row and that column, anyway, your automatic negative signs would be on the first and last terms and not the middle term. I mean, we don't do that. We don't do that. For a cross product, we do what we do. But I'm just sort of explaining some other math. When you're doing determinants, what are these plus, why the automatic negative sign? I'm sort of explaining. I still haven't really explained why does this array have these signs sort of attached to them. Innately, this determinant sort of has these elements of a determinant have these signs sort of attached to them for the purpose of expansion by minors, I guess. But I'm not sure why that is. So I've sort of previewed our main use of the cross product you got two vectors, I'm looking for that perpendicular vector, I'm looking for that perpendicular vector, and so I do a cross product. Usually it's in the context of searching for planes, which again is coming up in 11.5. But when you're in 11.4, you're not there yet, and so we come up with some other reasons to do cross product. So there is some, I think my homework assigned, well, they might say this, please find a vector perpendicular to both. You do a cross product. They might say this, find the area of the parallelogram. And so maybe you'll do a cross product and then find the magnitude, you'll get the area of the parallelogram. I'm just suggesting that this is in the homework, but I've got more important fish to fry coming up here, and I don't think this is on my test. But you need to get used to doing cross products, so you need to do a little 11.4 homework, and you got some context. Here's one, though, that I do put on the test. Check this funny guy out here. This is called the triple scalar product. The triple scalar product. This is when you have three vectors. You have u, v, and w, and then the triple scalar product is this: u cross v dot w. Now, let's think about this. I guess I should put parentheses on here. But I got three vectors, and so these are three different vectors. Three different vectors. They're not necessarily perpendicular to each other or anything. They're just three vectors in space. And if you want to do the triple scalar product, then you cross product two of them. And when you get that answer, that's a vector, right? When you cross product two vectors, you get a vector. And then you're going to dot product that with the other guy. And then that answer will be a scalar. And what's interesting is, and so maybe I should put parentheses on this, but I don't really have to, because maybe how math, you're supposed to work left to right. Also, it doesn't really make sense the other way. Look at this, you guys. If you happen to do the dot product first, watch. The dot product is a scalar, then how do you cross a scalar with a u? See, it's almost like we got three kinds of multiplication now. I hate to mess with you, but you know, if I have a 6 times v, we all know that's a scalar times a vector, and we know how to distribute it through, and it makes it 6 times as long. Anyway, that's a scalar times a vector. I can use a dot or not a dot, right? It's next to it, it's multiplied by it. Now, when I'm multiplying two vectors, I either use a dot, which results in a scalar, or I use a cross, which results in a vector. Yeah, that's all good to know. But anyway, I'm trying to imply that without parentheses, you got to work left to right here. I'm going to put the parentheses on there anyway, though. I mean, that's how you do it. But here's what's interesting, too. So this ends up being a number. And that number could be positive or negative, I guess. If I put absolute value on it, then it's positive, okay? So then it's a positive number. And then it could be, then this is interesting. It could be u cross w dot v. Or it could be v cross w dot u. I mean, it's interesting. It's all the same. Okay, but it's not always all the same, right? Without absolute value, one of them might be 28, the other one might be negative 28. The other one might, so I don't, but with absolute value, they're all the same. They're all 28 or whatever number it is. And here's what they are. This is funny. It is, with the absolute value on there, then it's a positive number, and it is the volume of the parallelepiped parallelepiped formed by the three vectors, formed by u, v, and w. Anyway, that's weird. Have you ever heard of a parallelepiped? Say no.
No.
You've heard of a parallelepiped. But as we've described and discussed a few times, two vectors in the plane, not in 3D, but just two vectors in a plane do form a parallelogram. You know, two vectors kind of can form a parallelogram when you start moving them and putting heads on them. Well, when you have three vectors, then you sort of form a 3D parallelogram. And a 3D parallelogram is like a parallelepiped. Here, I'll draw a picture of one. It's kind of like that, except I don't want to mislead you. This third vector is not necessarily, no, hang on, I don't want to mislead you. It's just three damn vectors, u, v, and who knows what kind of angles they make with each other. Look, here's w. It's just w is just a third vector in space. Look, here's w. Are you with me? So nobody's necessarily perpendicular to anybody. There's just three vectors with their tails together. But you can make a, what, I need all my colors here. If I put u on top of v, that goes here. Then I put v on top of u. I sort of form the base of this thing, maybe you could say. And then if I take these w's and put them all on all these corners, again, keeping them the same length and keeping them the same angle, then I can put this v, I can move up here to this v, and then that u could be that u and that u. Anyway, there you got a 3D box. It's a box, but it's a hell of a weird box. It's a box with not necessarily any right angles. Parallelepiped. I mean, when you draw it, it almost looks like it might have some right angles. Maybe, you know, it almost, I didn't intend that. I didn't mean that. And here, let's do this. So in this room is like a box but it's full of right angles, right? It's all 90-degree angles everywhere. Okay, so how do you, watch this. To make this room a parallelepiped, here's what we'll do. Take those two walls, watch me, I'm taking those two walls and slant them like this. Okay, now that's kind of cool. Now I'm going to take these two walls and slant them like this. Now my base is still a rectangle though with right angles. So to generalize this and say it's not, then I got to grab that corner and sort of pull them in and make the base not right angle. I mean, I'm saying if it is right angles, it's still a parallelepiped, but I'm trying to generalize it. They don't have to be right angles, so it can be this hell of a tilted box. Tilted in all sorts of ways with no right angles. And the volume of that is a triple scalar product. So it's kind of fun to do a triple scalar product. I think they say when you do a triple scalar product, you can replace the IJK. Huh. Hang on a second. Let's just try one. I'm just going to make one up. Here's U. 3, -2, 4. Here's V. 1, 0, -6. Here's W. 8, 2, 1. So I got 3 vectors. Just made them up, you know. But I bet they don't. Nobody meets at right angles. You know, I don't know what they do. I want to do the triple scalar product. I want to find. Here's my question. This is a quiz question sometimes. Find the volume of the parallelepiped formed by these 3 vectors. So basically, you got to do this. And you can pick whichever one you want to do. I said it doesn't matter. What this says is that you got to cross product 2 of them and dot product the other one. And if you throw absolute value on there, then it won't matter which ones you pick. I think I'll just cross product those 2. To do a cross product, I got to write it all out. I can't really do it in my head. I gotta do my IJK. I gotta do my 3, -2, 4, my 1, 0, -6. It's nice to do a cross product with a 0 in there. That kind of helps things a little. Well, we'll see. I should be able to knock out this cross product. You guys are just getting used to this, but you should be able to do it. 12 minus 0, is that how you do it? 12 minus 0. Then when you move to J, you cross out J's column and you're doing this minor determinant. -18 minus 4, -18 minus 4, -22. And then you get to K. Oh, wait a minute.
Forgot the negative.
I forgot my automatic negative sign. Thank you very much. So it was -22. J comes with an automatic negative sign. It should be +22. Thank you for catching me there. And now K. We move to K and we get 0 minus -2. You guys got to watch that. Subtracting a negative always gets you. That's a +2, I guess. 0 minus a -2 is +2. And ta-da! Wait a minute. That's the cross product of U cross V. Now I want to dot product it with the 3rd vector W. So I guess I'll just do this dot product here, if you don't mind. There it is. That will be some big numbers. 96 plus 44 plus 2. And you add that up, and if they happen to be negative at the end, you would absolute value it. This one happens to be positive 142. We had no units on this, but it is the volume of the parallelepiped. It's 144, whatever the units are, cubed, I guess. Whatever. The volume's 142. We did a triple scalar product. If you did it in some other order, it would be the same. It would work. Should get 142. Remember when I did that? When I did that cross product the first time, it's getting messy up here now, but hang on a second, I want to say something. So when I did this 12, I'd do this little minor determinant, which is 12 minus 0, so it would have been 12 times I. and I could write 12 times I, the vector I, the unit vector I, but instead of writing 12 times I got this notation. But that is 12I, and then that's 22 times J, and then that's 2K. That is what it is. So it's like he's multiplied by I, he's multiplied by J, he's multiplied by K, which happens to be this top row. Now watch this. So then if you're going to dot product him with W, you're multiplying him by 8 and him by 2 and him by 1. So one way I've seen this presented in the book, although I did it like this. I did a cross product, I forgot my answer, I did a dot product. But if you replace this I, J, and K with 8, 2, 1, then you're doing this minor determinant and you're multiplying it by 8. And then you do the next minor determinant and you multiply it by 2. And then you do the next minor determinant and you multiply it by 1. I mean, you end up multiplying this by 8, multiplying this by the 2, and multiplying this by the 1. So if you do this, you're doing the dot product, you're doing the triple scalar product all in one move, kind of. Doing the dot product as you do the cross product with you. It's interesting. Yeah, okay. All right, well, you know, I got 10 minutes. I was going to quit. I kind of want to quit, but before I quit, I'm going to do one more problem. So now I'm just backing way up for a second. I'm just not way up, but this was good. This was a good introduction to the cross product. You should work on this homework. But before I leave, let me back up, and I just found this question. This is in the book, and so this is back in 11.3. It's concerning the dot product, I guess, and it says this: find the angle between, I could just read it to you. Find the angle between a cube's edge and its diagonal. Let me just make sure I got this right. Hang on. Find the angle between the diagonal of the cube and one of its edges. Find the angle between a diagonal of a cube and one of its edges. Maybe I should say it like that. Find the angle between the diagonal of a cube and one of its edges. Diagonal. So that's a good question. I found this in 11.3. It happens to be number 57. I assigned it. It's a good little problem. Find the angle between the cube's diagonal and one of its edges. I know the cube and one of its edges. Okay, cool. Anyway, when they asked me to find an angle, I'm back in 11.3. You need this formula. I like this. This is on my test. This is on my quizzes. That's this formula again. But to find an angle, the cosine of an angle between two vectors is u dot v over the magnitude of u and the magnitude of v. Now that's the angle between two vectors. This question is talking about the sides of a cube and the diagonal of a cube. Well, I guess I'll try to treat those as vectors. I think I should try to think about those as vectors. Let's draw a cube, and I don't know, maybe I shouldn't just draw a cube, but I should maybe also draw a cube in a coordinate system, in my coordinate system. That is a terrible cube. That almost looks like a parallelepiped. Anyway, well, you know, this might make more sense if I put this on my XYZ coordinate system. Here, let's make that the origin. Therefore, this is the z-axis. This is, of course, the y-axis, and this is the x-axis coming out at me. And there's a cube sitting there. If there's a cube sitting there, you know what a cube means. What does it mean? All the sides are the same. That's what makes it a cube. It could be a rectangular solid. A rectangular solid would be a box where not necessarily all the sides are the same. But when you say the word cube, all the sides are the same. So I don't know, you could pretend it's 1 by 1 by 1. You could pretend it's 2 by 2 by 2. You could pretend it's A by A by A, I guess, if you wanted to be more general. I don't mind just putting some ones on there. Let's call it 1, 1, 1. I'm going to call it, it's a 1 by 1 by 1 cube. So I need the angle between the diagonal and one of its edges. But I got this formula for the angle between two vectors. So I need to think of the diagonal and the edges as a vector. That's what I need to do, which is not a huge stretch. So can you tell me, with this cube, what would be his diagonal written as a vector? Very easy.
1, 1, 1.
Thank you very much. His diagonal, from the origin, his diagonal would be out 1, over 1, and up 1. When I draw it, it kind of disappears. You can't see it too well, but he's coming out at you. That's the diagonal of the cube, and its vector representation could be 1, 1, 1. I want to find the angle between that vector and one of its edges. The word edge is, an edge. This edge would work great. This edge would work great. This edge would work great. By the way, without doing this problem, you may be tempted to say 45 degrees, but it ain't right. It's not 45 degrees, I don't think. Anyway, which edge do you want to use?
X-axis.
So let's use this edge. So that's a little hard for me to draw that angle. Thanks a lot. Anyway, it's that angle then between the diagonal and its edge. But you're right, that edge then would be another vector, which I'm going to call what?
1, 0, 0.
1, 0, 0. 1, 0, 0. The x-axis. The x-axis written as a vector, so to speak, is that. Cool. Let's do the little formula here real quick. The dot product over the magnitude of each, the cosine of the angle, is the dot product. The dot product is so easy. What's the dot product? The dot product?
That's just 1.
Thank you. 1 over the magnitude of him. What is the magnitude of this one? What is the magnitude of you?
Square root of 3.
Good. The square root of 3. 1 squared plus 1 squared plus 1 square root of 3. And and that's multiplied by the magnitude of the other one, which is
1.
1. And there you go. I want the cosine inverse of that. Right. The angle is the cosine inverse of 1 over the square root of 3. I pick up my calculator, and it's about, I don't know, what is it, 57 degrees?
It's 0.955. Oh, wait, I have the radians.
Oh,
Sorry.
0.955 radians. That is about 55 degrees.
54.7.
54.7 degrees, yeah. I mean, maybe that's a famous angle. Well, maybe it's a famous angle. Maybe it would be like a bond angle in chemistry. You think these things, I don't know, there's another question involving bond angles in chemistry. That might be a different question. But that's interesting, right? It's not 45. It's obvious it's not 45, but it's, by the way, that's 54.7, that's 54. Yeah, the cube and any one of its edges, the diagonal and any one of its edges. So it wasn't a hard question, but it's, I don't know, you got to think. You got to make vectors. Draw pictures and make vectors. And they weren't hard, but there's another one like that. There's 58, and there is one about the bond angle, 73. That's worth discussing. That's a good one, too. So that's back in 11.3. I'll quit today, though. I'll see you Wednesday. I think I'll help you with some more homework. Maybe I'll ease into 11.5 Wednesday, or maybe I'll wait till Friday to ease into 11.5. We're off Monday. You know, I'm thinking the first quiz might be the next Friday, probably.